So yeah, so today's a makeup session for the session that we missed on Tuesday. Basically, today we'll be covering week 8, the content that was covered in week 8. So before doing any of that, let me again start with the introductions. Okay, this is recording. Fine. So yeah, so the introduction is sorry, the course name is Analog VLSI Design. All right. Course name is Analog VLSI Design. It's an NPTEL MOOC course. The instructor for this course is Dr. Iman Mandal, Assistant Professor in Electrical Engineering Department at IIT Kanpur. Myself, my name is Mayank Anupam. I am a PhD student in the Electrical Engineering Department of IIT Kanpur, and I hold these discussion sessions for the course Analog VLSI Design. All right. So in week 8, this is a brief summary of what was covered in week 8. So mainly we focused on handling the this thing, a non-ideality, right? We used to assume that a MOSFET has infinite output resistance, right? No parasitic output resistance. That is what we want to assume. We were assuming earlier that a MOSFET is an ideal element which does not have any output which has infinite output resistance. However, that approximation or assumption doesn't seem to hold true in real cases, and in the real MOSFETs you have some output resistance at the MOSFET, right? So this is what we were mainly focused about. We saw how what is the reason behind having that output resistance in a MOSFET. We saw that, and that comes because of a physical phenomena called channel length modulation. Okay, so we reviewed what we saw quickly what is channel length modulation. Okay, from a very top level perspective, we are not going to go into details of that in this course. If you want to learn about channel length modulation, how does it impact, and from where does it happen, how does it really happen, you will have to look for courses in device physics. Anyway, so we know for us only thing that matters is that there is something called channel length modulation, and because of that there is some finite output resistance. Now that we have finite output resistance, our next goal in this course was to design. So basically earlier we were assuming that output resistance is infinite. So now that we have output resistance, some finite output resistance, how do we deal with it so that it does not negatively impact our circuit's performance? So for that we introduced some new circuit topologies, mainly cascode, current mirrors, cascoding basically. Cascoding is from a very in a very generic sense. If you someone asks why do you do cascoding, so the first answer should be to simply increase the output resistance of any MOSFET, of any this thing. So cascode basically increases the output resistance. It's a basically any if you have any current source, okay, you can make it a better current source by simply adding a cascoding to it. So I'll discuss what do I mean by that. Sir, I mean, in the instructor also discussed about this in details, but I'll anyway go through it. So once we saw what is a cascode, so after that we looked at what are the swing limits in any cascoded device, in any cascoded topology, right? And after that we looked at variant of cascoding, which is wide swing cascode current mirrors. So we looked at it also, basically, which it could tolerate much larger swing at its output compared to a simple conventional cascode. Fine. Before going into the problems which I want to discuss in this session, I want to ask you. So, like Nikhil asked me in the discussion forum, he had something to ask. You have something to discuss with me, right? You have some doubts. So tell me what are those
Yes, man.
doubts?
Actually, like I have gone through that videos twice. Then I have understood got some clarity actually on it
Oh,
for some
anyway.
solving that week nine's assignment.
Acha, acha, okay. But
That's it.
anyway, so do you have anything else? I mean, any question you want to
Like
discuss?
in general, I have one question is like, see, if anybody asks MOSFET is a like what type of a device? So we generally say that it is a VCCS, right?
Yeah, it's
Like,
a VCCS, correct? Yes.
but we are by doing that what you called all variations, right? VCC, VCVS,
Huh.
CCCS.
Huh. Correct.
Then why it is only called as
Yeah. So do you know the answer of this, or do you want me to say? What do you think is the answer to this?
like different types of biases give different types.
Correct. So I told you na earlier, I mean, I discussed this in the first or second class itself, that if you have any one of the device, like any one of the control sources, if you have out of the four, we have four, right? VCCS, VCVS, CCCS, and CCVS. These are the four different types of control sources. So as I said in the very first or second session, I told that if you have any one of these, okay, you can generate the remaining three from by using any one of these. Okay, that's how it is. They can all be generated by using one of the device.
Okay, so
MOSFET
MOSFET is
MOSFET
generally
by
a VCC.
default MOSFET by default, it's a device operation is such that it acts like a VCCS. A VCCS is the best model, best this thing best circuit to sorry, best device to model the behavior of a MOSFET. Okay, a VCCS is the best thing that we have to model the behavior of a MOSFET.
Like VCCS we get only in common source configuration, right?
No, no, it's always a you see okay, what else do you think?
Like VCCS it is applicable only in common source, right?
Okay, let's do that. So this is MOSFET. So there are three, right? It's a common source like this, right? This is common source. Then there
Yes,
is common drain, right? Where this is like this. These are the terminals. So this is common drain, and then there is common gate, correct?
yes, yes,
Where you have this thing here and this thing here, right? You have these two conditions. So this is common gate. These three you have, right?
yes.
Now, yeah, you correctly pointed out that this particular whatever I'm saying, I'm actually talking about mainly common source only. Yes, I'm mainly talking about common source only. So in the common source mode, yes, it is acting as a VCCS. In the common drain mode, it is acting. Tell me what does it act like in common drain? So what does the behavior of a common drain uh, bias MOSFET is? Tell me.
CCCS.
No, it's a VCVS. Okay, so this acts like VCCS. This is VCVS, and this guy. Tell me, what does it look like?
CCCS.
Yeah, it is a CCCS. Fine. Yeah, you're correct. You're correct. So there is something else called a CCVS. Okay, so it acts like a CCCS here, but this guy, but you can generate a CCVS also from this one only. That is something else. So that ignore it for now. But yeah, as I told earlier, that even if you can use the MOSFET in only one configuration like this, you can generate all the other types of controlled sources using MOSFET in this manner also. Okay, this I talked about in the first session itself.
Okay, man. Thank you.
Okay, and yeah. So anything else, Nikhil?
No, no, no. You can continue.
Okay, fine. So okay, in that case,
And
um,
one more thing is like,
yeah,
what is difference between normal gain and intrinsic? Are they same or different?
normal gain, intrinsic gain.
Yes.
So intrinsic gain of a MOSFET, when you say, so let's say you have this thing. So this is RL, and let's say it also has some output resistance. Okay, R out. I've just shown it here. So what is the gain from input to output? VO by VI, small signal gain, is how much? GM times
minus GM times R.
R L parallel
Well, R out.
R out. Correct? Yeah. Now tell me, this is the total gain, right? From input to output. But you see this, what is the gain of only the MOSFET if you had seen? So let's say RL becomes infinite, this RL guy becomes infinite, then what is the gain from input to output?
Minus GM times R. Sorry,
Yeah,
R out. R out.
yes, it is minus GM times R out only.
Yes.
So intrinsic gain of a MOSFET is basically the gain of only the MOSFET from input to output. When the output load is assumed to be infinite. Okay, in that condition, what is the gain of the MOSFET? That is the intrinsic gain of the MOSFET. Okay, the intrinsic gain of a MOSFET is simply GM times R out for a common source. This thing for common source configuration, the intrinsic gain of a MOSFET is simply minus GM times R out, nothing else. It's basically the gain of the MOSFET, assuming that the output load is infinite. That is what it is. Got it?
Yes. So basically, intrinsic means like we need to make a load equal to infinite. Like
Yeah,
that.
intrinsics, as the name implies, it is simply what is intrinsic means what? Whatever is the is only because of the device itself, right? There is nothing else which is present. Whatever is because of the device only, that is only called intrinsic. What is the name? The name itself is very evident, right? The meaning should
Yes.
be very evident from the name itself. Yes, so this is the difference between intrinsic and, so this is the intrinsic gain, and this is total gain. Okay. Yes. So anything else?
No.
Good. Fine. So, now let's briefly discuss something about cascode current mirrors. Okay. I want to discuss something about cascode current mirrors. Then I will go on to the problem. So problems, I will simply discuss the problem that is already there in the assignment. I will simply discuss that only, because that I think is enough to make my point. And if you do it diligently, you will be able to understand everything. So, yes. By the way, there was a session yesterday, right? With the instructor. So, did you attend?
Yes, man. I have attended it.
Okay, so how was it?
It was good. Like we could have asked direct questions.
Yeah, so did you ask some
It,
anything,
it,
any
yes,
doubt
yes, I
that you
have
have?
asked.
Okay, good.
Like
Okay.
these sessions, like with the instructor, will be there from here onwards, or like
No, no,
it
it
is
was
mentioned in the discussion
once,
form.
no, no,
Like
it was
sorry.
only once.
Okay, once. Okay, thank you.
Yeah, fine. So cascode current mirrors. Now let's try to, I will try to shed some light on it. Yeah, so stop me at any point if you are not able to understand something, okay? Anyway, so how did we learn about cascode current mirrors? So we said that, by the way, we know what are current mirrors, right? Current mirrors is very easy to understand. We already know about them. But cascode current mirrors is something which we want to appreciate. So for that, let's draw simple current mirror first. And let's say this goes to some load. So this is, let's say, I naught. M1, this is M2. So if this is I naught flowing into this guy here, this I naught is flowing here. So what is the current that is going to flow through this guy? If I assume that the channel of modulation is not present,
Same I naught will
same
flow.
current, right? There is no doubt there. If this is I naught, this also has to be I naught. This is under the assumption that,
W by L everything properties are.
yeah, assumption. So that, yeah, so that I should have mentioned here. So W by L is same for both. So W by L M1 is equal to W by L of M2. That's good. Fine. So this is under the assumption that CLM is not present. Okay. So now let's assume that CLM is indeed present. What happens? So this is case 1. Hmm. So now let's talk about case 2, where the CLM is indeed present. Okay. Tell me what is going to happen. If CLM is present, can we still say that the currents at both places will be I naught only? I mean, is it possible or not? Current to be same in both the branches. In both the MOSFETs, the current would be same. Is that statement true or not? Can it ever be same or not?
It can be same, I guess, provided if RDS1 is equal to RDS2.
No, no. RDS1 will be RDS1 will always be equal to RDS2, isn't it? So RDS1 and RDS2 will be same, right? This is RDS2. This is RDS1. So what is the formula for RDS1 and RDS2? So RDS is what? 1
1 by
over
lambda times ID set.
ID,
ID
right?
set.
SAT or ID? Lambda ID, right?
Yes, yes.
Huh. So yeah, tell me something. So basically, you are saying that if the current is same for both, so RDS is same in that sense, right? But that's like flipping the argument. So that's like that's not a correct way to argue. See, okay. So can it ever be same? So you said that RDS1 is equal to RDS2. So that's okay, but mm, that's not a very good way to argue. Okay, a better way to argue would be, yes, they can be same provided. See, for a MOSFET, current depends upon what? Current depends upon mainly the voltages at three terminal, right? The voltages at three terminal, right? Because the body is assumed to be potential for both the MOSFETs. So here there are only three terminals which we are concerned about. What are those three terminals in a MOSFET? Tell me.
Gate, source, and drain.
Drain. Yes, correct. So in a MOSFET, the total current, which is ID, is a function of gate voltage, drain voltage, and source voltage. Right. Now, can you look at these two MOSFETs here? So other than so basically these are the voltages that is a function of, right? Other than this, it will also be a function of W by L, mobility and all. So, but that we assume to be assume that it is the same for all the MOSFETs. Okay. So now the only thing that can vary is gate voltage, drain voltage, and source voltage. So if you look closely at these two MOSFETs here, what do you think are different in these two MOSFETs? Which voltages are different? Can be different.
Like in the left side, drain and gate are same, but in the right side, they might be different.
Correct. So basically, the gate voltage is same for both, right? You see, gate voltage is same for both because gate is connected to the same net, right? Gate is same, source is same for both. The only thing which can differ is the drain voltage, correct? The only thing that can differ is the drain voltage. Now, why was this not a problem here? Here also drain voltage can change, right? For the two MOSFETs, but still we ended up saying that the current will be same for both the MOSFETs. Why is that the case?
There, I think that like those values are taken as like think
No,
like
see, yeah. So basically, this thing, the current becoming a function of gate voltage, drain voltage, and source voltage. In this, the current becomes a function of drain voltage only when channel length modulation is not there. Okay, sorry, channel length modulation is there. Only then the current becomes a function of drain voltage, isn't it? If the channel length modulation itself is not present, then the current is not a function of drain voltage, isn't it? We know that in the absence of CLM, the current here is what,
gate voltage and source voltage
isn't it?
function of.
This is the equation, right? So it's not a function
Yes,
of drain voltage at all, isn't it? So only when the CLM is present, only then there is a possibility that the currents in the two branches can differ here, right? Because the drain voltage itself here is not same for both the MOSFET, right? So still you can ensure that the current is same for both the branches when the drain voltage itself is the same for both the branches, isn't it? So if the drain voltage ends up becoming same, then also you can say that the current will be same, isn't it? If the voltage here is VD1 and VD2, then ID1, right? So let's call it ID or I2. Okay. So I2 will become equal to I naught. So here I2 will become equal to I naught when,
VD1 equal to VD2.
yes, when VD1 equal to VD2. This is the whole point that I'm trying to make. See, in this MOSFET, even when the channel modulation is present, the currents in the two branches of a current mirror can become equal when the two drain voltages are equal. Got it? And this is the whole idea behind pushing for a cascode current mirror. This is another way to look at cascode current mirror. Okay. So here basically what is the problem? Now drain voltage here at this place, it is very difficult to control, isn't it? Because this is something which is connected directly to the load, right? Isn't it? And the moment there is some current in this, right, the drain voltage and the load, let's say that the load changes, then basically your voltage at this place also will change, isn't it? Which simply means that the current mirroring will not be proper, correct? Isn't it? So to deal with that, to basically make sure that the voltage VD2 does not become very strong function of the load or the output current itself, for that what did we do? We added another layer of protection here. So this is what it is. This is case 2. Let's go to case 3. What did we do in case 3? In case 3 we simply took a MOSFET like this. So the current is like this. Then there is MOSFET here, another MOSFET here. Hmm. Okay. And then this can be connected to, let's say, RL or whatever load. Let's say this is VD2 or VO. This is let's call this M1, M2, M3, M4. Okay, fine. This is not a very good way to draw. It's very messy. Hmm. Okay, fine. So this is now this is V out. Okay, let's call this VD1. Let's call this VD2. Okay, let's call this V out and let's call this VD3. Now, what is happening is, you see, uh, this is I naught. Now tell me, if you only look at this branch here, there is still a current, this thing, diode connected devices are here, right? I mean, gate and drain are shorted in these two MOSFETs, right? Now tell me, which transistor actually sets the current in this branch? In the second branch, which transistor actually sets the current? Who is the guy who is dictating that this much current has to flow in this branch? Who is that guy?
In the left branch or right branch?
Right branch. This branch. I'm talking about this branch.
Here first M2 will set actually.
Yes, exactly. Right. So M2 is the guy. It is setting the current in the second branch. Right. Okay. And if you can look at it closely, the gate of M2 is being controlled by the gate of M1, right? I mean, they are connected together, isn't it? So whatever gate voltage is being sensed by M1, the same voltage is being fed to M2, isn't it? So what I'm trying to the point that I'm trying to make here is that the current in the current in the right branch is being controlled by M2, which in turn is being controlled by M1, right? The current, so you can say that the total current that is going to flow through here is somehow being controlled by M1, isn't it? Okay. Now that you have understood this, the M1 current, for the current in M1 and sorry, for the current to be same for M1 and M2, what has to be same? If I want to
Gate
make sure,
voltage and
what? Go again. If I want to make sure that the current in M1 and M2 have to be same, so what all things have to be same?
gate
Basically,
voltage and
gate
drain
voltage
voltage.
is same, right?
Yes.
So drain voltage has to be same, right? I am calling current in M1 to be IM1 and current M2 to be IM2. Okay. And we know that the current flowing through M1 is how much? I naught, right? This is I naught, right? So same current
Mayank,
will flow.
I have a question here.
Yeah, Sakya, come on.
So why it needs to be same. But V D2 needs to be just uh, the value of VGS minus threshold, right?
No, no, I'm
This
talking
is the
about the
requirement.
case where there is a CLM.
Okay, so if there is a CLM, then
Uh,
it has to be same.
so if you want to make sure that the current is same in both the branches, I'm talking about current mirrors. Okay.
Okay, yeah, that is what I did mistake.
Uh,
Okay,
so
okay.
this is the current mirror I'm talking about. So in the current
Mhm.
mirrors, you want to make sure that the current has to be same, right? That is what you ensure in the current mirrors. So either you
Okay.
want the current to be same in the current mirror, or you want it to be a multiple of whatever current is whatever current is flowing here, right? Either you want the current in this branch, let's say call it.
Yeah, I am interrupting you again.
Hmm,
So on the left hand branch M1, so it is in
yes,
saturation, right? Always.
yes,
So the saturation current is flowing through that. And
yes,
similarly, if you are saying that the M1 is setting the M2,
huh.
then the current there also will be the saturated current if it is same transistor.
If every transistor is in saturation, yes, it will be
Yeah,
saturation current only.
it
Yes,
is our assumption that M1 and M2 are similar.
yeah,
So
yeah, they are similar, correct.
so the saturation current.
Yes.
Now, the my point is, if it is saturation current,
Hmm.
then our transistor should be biased minimum in that state to get
Hmm.
that saturation current, right?
Yes.
So forget
Yes.
about everything. Just M2. If I give a gate voltage and it is
Hmm.
the source is already grounded, and VDS should be one threshold below the gate voltage. That is the saturation condition.
Yes.
So that in that case, VDS VD2 should may not be equal to VD1.
Okay. So,
So this is my assumption basically.
yeah, yeah,
So
it may
while
not be equal.
VD2 may not be equal to VD1, but
Yes.
you are writing here that to get the same current, we
Hmm.
need VD1 equal to VD2.
Yes. So, as I already talked about it, what why if there is channel of modulation is present here, okay, then the current is a function of what? When will these two currents be same in that case? The current through IM M1 and M2. When these two currents will be same if there is channel modulation. So if any device is there, you want to make sure that the current flowing through the two MOSFETs has to be same. Okay, and we know that the MOSFET is being controlled by three terminals, right? Gate, drain, and source. They are the three terminals which control the current through the MOSFET. Now, if no one knows anything about the device physics also, it's just, let's say we only know that there are three design variables. Okay, there are three variables which control the current in the device. So if you tell it to someone who does not know anything about engineering, sorry, who does not know anything about MOSFETs, but he only has a black box. Okay, there are two black boxes, one has M1, one has M2, and he said that make sure that the current through both of these black box is the same. What will he do? What will he or she do? He will simply connect the same potential to across all the three terminals, right? For both the black boxes, isn't it? The two currents have to be same, which means that all the conditions which are experienced by M1 has to be ensured for M2 as well, isn't it? Voltage wise,
Yes,
right? Am I wrong or right?
yes, yes.
Yeah.
It is
So
black box.
yeah.
Okay.
So let's say that is what I'm trying to explain here is that it doesn't because M1 and M2 are two devices here. So when will the currents be exactly same for both? It will only happen when the terminal voltages are same for both, right? Otherwise, the currents will may not be same, isn't it? In any condition, you know that the current through a MOSFET, when channel modulation is present is what? So IDS is equal to what?
Okay, so you are saying that if we change the VD2, then the channel length modulation condition will be changed, and that's why the current will not be same.
So this is something which you know, right?
Lambda VDS.
Isn't it? This is what you know. So let's say for these two MOSFETs M1 and M2, what all things are same for M1 and M2? We know that W by L is same, right? You also said that W by L is same, right, Sakya?
Yes, yes,
Yes. Mu and Cox are same for both, right?
yes,
VGS is same, right? Because
yes,
gate voltage is same for both M1 and
yes.
M2. So the only thing that is not same that may differ is what? This VDS, right? Drain to source voltage.
Okay, okay,
So if
okay.
drain to source voltage changes for both the MOSFETs, the current will change na, in both the MOSFETs.
Yes, 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 yes.
Yeah, that is what I'm trying to say here. Is that for making sure that the current is same in both the branches, you need to ensure that the drain voltages are also same for both the MOSFETs, isn't it?
Yeah,
This is
yeah.
when the
Thank
channel
you.
length modulation is present. Okay, now having said that, it is not possible to control the drain voltage here, right? You know that the drain voltage, to make sure that the drain voltage of both the MOSFETs are same, it is not really possible because the drain voltage at this point is also controlled by what? By the because this guy is connected to load, right? And load resistance can change, and a whole lot of things can change here at the output side, isn't it? This side in the right branch. So because this guy here, this is connected to the load, to some load, not just RL, it can be any load. And based on the load condition, the currents, the voltage V naught can change here, and because of which VD can change here, right? The drain voltage can change here. So that is why it is not really possible to ensure that the drain voltage for both the MOSFETs are same always, right? However, I'm not going to that. I'm saying that let's say in some universe you are able to ensure that VD1 and VD2 are same. Then the currents will be same for both, right?
Yes,
Yeah. This is the whole point I'm trying to make. After this, I'll come to the next point. So is this understood or not? That for same current to flow in both the branches, in the presence of CLM, we need to ensure that the drain voltages are also same. Correct? This much is understood. Now, how do we do that, and how do we avoid how do we reduce the effect? So, effect of this load on this drain voltage is what I'm going to discuss now. This is what we do in cascoding. Okay. So, as I just pointed out, is that this drain voltage VD2 is not in our control, right? It's basically changes with the load requirement, right? As you change the load, the voltage V naught here will change, and because of which VD2 will change. Correct? So the way to avoid is by simply adding this extra layer here. Okay, the extra layer of M3 and M4, this acts like a shield in between. Okay, now this is how you can understand it. This guy here, this acts like a shield. This is not a good color. This acts like a shield. Okay, shields what? The swing shields M2 and M1 from the, or let's talk only about this MOSFET. M4 shields M is a shield from shields M4, or rather M2, from the large voltage swing at V out. So what I was trying to say is that this V naught here, V out here, it will change, isn't it? So let's say in the best one of the most simplest example to understand how does it swing is that, let's say this V out is some sinusoidal voltage. Okay, let's say it's some sinusoidal voltage. So V out will change, right? According to sinusoid. However, you do not want the current through it to change, isn't it? Let's say you do not want the current through it to change. Let's say it is some voltage changes there, it's changing between some range V out. However, you do not want the current to change through it. Okay, so for that you need to ensure that this drain voltage here remains fixed, right? Because as we said earlier also, the total current that is going to flow through the second branch is being dictated by M2, right? So as long as the voltage terminals across M2 remains fixed, we have nothing to worry about. The current will always be same. Current through this branch will always be fixed, right? So for that only we add this extra layer of protection, this M4 guy. What does it do? How much ever is the swing here, okay, it will simply reduce that swing. So let's say this guy at the output side V naught was moving between these two levels, okay, these two levels. However, because of
Mayank,
M4,
can you explain once again this one?
yeah, I'm let me finish it, okay, then you can say some, then again tell me if you didn't understand, okay. Yeah, so I was saying that okay, let me repeat what I'm saying. You see, for as I talked about it earlier also, Nikhil, right? So you said only that this the current through the second branch, the current through the right side branch, right? It is dependent upon what? It is being set by MOSFET number M2, right? It is setting the current in the second branch. MOSFET
Yes, yes.
M2 is setting the current in the second branch, isn't it? Okay. Now that we know that, let's say uh, when can the current through the second branch change? The current through the second branch can change only when VD2 can change, right? Because VG1, this guy here, it is already fixed, right? This guy, this voltage, the gate voltage of M2 is always fixed, isn't it? Because the left branch is not changing. Okay, this left branch, nothing is changing here. There is nothing which can change. The current I naught, you assume that it is remaining fixed. So the only thing that can change is what? This drain voltage, right? And because of that only the current through M2 can change, isn't it? Right, Nikhil?
Yes, yes.
Yes. So if I can ensure that the drain voltage at M2 does not change, even when the voltage at, sorry, even when the voltage V out changes, V naught changes, even then if the drain voltage at M2 does not change, if I can ensure that, then I can say that the current through the second branch is also not changing, right? Is that point understood? I would like to get some yes or no at this point.
Yes, yes.
Yeah. So what I'm saying is that this current through V naught, sorry, the voltage V naught can change. We cannot, because we cannot control that, because it is connected directly at the output side. There can be some load. Okay, load can change. So because of that, V naught can also change. We cannot do anything about it. However, something if we can do between V naught and VD2, if we can do something so that whatever change is happening at V naught does not really impact the voltage VD2, then we can say that the current through M2 is remaining fixed, isn't it? And since the current through M2 is also the current through the whole branch, whole second branch, we can say that in that case the current through the second branch will also remain fixed, right? Now the way to achieve that is by adding this MOSFET M4. What it does is that it reduces the swing, it attenuates the swing from V0 to VD2. So one way to understand is that, let's say V out changes between these two levels, okay, between V1 and V2. Okay, let's say V out changes between V1 and V2, And because of this M4, what will happen is VD2 will change between only small level or small this thing levels. The level change will be very small. So this will be, let's say, V1 prime, V2 prime. So what will happen is, because of M1 and because of M2, V1 minus V2, or rather V1 prime minus V2 prime, will be much smaller compared to V1 minus V2. So what effectively happens here is that because of this M4, the large change in voltage at the output is converted into a very small change in voltage at the drain of this MOSFET, which is what our goal was. Is that point clear? I mean, were you able to understand that?
Yes, yes.
Okay, so Nikhil asked me, right? Nikhil, were you able to understand that?
Yes, yes.
Okay, good. So if you're not able to understand, you can ask me, because this is a very crucial point. Okay, this is the whole point that I was trying to make today, that I wanted to make today, is that the idea of adding this MOSFET is to simply shield this guy, the second the, the 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 MOSFET which is below it. It simply shields the MOSFET which is below it from the large swing at the large swing that it faces at its drain. Okay, this is one way to look at the cascode. Fine, if
Okay.
you've understood, then it's fine. Because now the idea is very simple. Okay, now let's say this is not enough for you. You want to make a even better this thing, because see, there is some swing, right, at the output side. You have large swing, and that is reduced to very small swing here, right? But still there is some swing here, right? Let's say you're not happy with that. You're not happy with this performance. So what you can do is you can go one step further. What you can do? Tell me. What can you do? You want to make a even better current mirror. What will you do? You can do this. The thing that was given in your assignments also. So now tell me, in the right branch, who sets the current? Who sets the current in the right branch?
M2, M2.
Yes, this guy sets the current. And here, as you can very easily see, is that looking from the same, arguing in the same manner, whatever is the swing, let's say swing here is this much, okay, at the output side, at this side it will be reduced to a small amount, okay, and at this point it will be even smaller. Okay, so that is not, uh, I'm not able to draw it very well, but let's say it is slightly larger, okay, then this will be very small. The swing at this place will be very small. So effectively you are at by adding each layer of protection, you're simply increasing the uh, basically you are increasing the immunity of the this current setting MOSFET to the output swing. Okay,
Okay,
so in another manner, it is becoming better and better current source. So current source is what? It has infinite output resistance, which means what? Whatever is the change. So what is the current source? What is a VCCS, or rather, what is a VCCS? A VCCS is you have some voltage here, right? And you have some current here. This is V. So let's say this is some K times, rather G times V, right? And this is some resistance here. Huh. So this is your input, right? This is your output. So this is a VCCS. So what is a VCCS? It's a simply a voltage control current source. So because of this voltage here, you are getting some current which is G times V, which is going to flow through this, right? And your goal is to make sure that all the current flows at the output side. So at the output side, you will like to connect some load, right? You like to connect some load. So the idea will be that you want to make sure that all the current flows through this only, right? G times
Yes.
V. So when will that happen? That will only happen when your R out is
Infinite.
infinite, right? And that so
Yes.
basically this is what you're trying to ensure here also. So
Okay.
from this side, if you look, if you see it from the below side, below the bottommost MOSFET, this is the MOSFET which is the current setting MOSFET, right? So this is the guy who is setting the current. This is the
Yes.
MOSFET who is setting the current. So
Yes.
For this MOSFET, this current has to travel all the way from here to here, right?
Yes.
From this place to this place. It has to travel to the load, correct? And
Yes.
this current does not have to be, I mean, this current should not be dependent upon the uh, voltage at the output side, right? This is the whole idea. So that is what you're trying to achieve here by simply adding more and more protection. You're simply boosting the output resistance. Now, so these are different ways to look at the problem itself. Anyway, so this is what I wanted to talk about. Now that this is clear, let's quickly look into the problem at hand. So this is the problem that was given to you in the assignment, right? So like, did you guys have any problem attempting the question? Because the solutions are already there. So I mean, I wanted to ask, do you guys have any special question regarding to this? How did you guys attempt it, by the way? So it is very first part is simple, right? How much should be the minimum V naught to ensure all transistors even in saturation? So that is very simple to do, right? Tell me here itself, what will be the V naught minimum for the transistors to be in saturation? How will you do it? How did you solve it?
3 VGS minus threshold.
Hmm. So here, basically, you have to assume it this way. So first you have to find out what is the gate voltage at all the nodes, right? First you have to find out what is the gate voltage here, here and here, isn't it? Once you find out what is the gate voltage here or at all the three nodes, you know that at minimum V naught, you it is very natural to expect that all the node voltages at this way, this node and this node, all will be minimum, right? Isn't it?
Yes. Yes.
Yes.
Yes,
So basically, what will be the minimum voltage here? This is VD sat, right? Correct? VD sat 1, right? And since all the transistors are the same, I think it will be VD sat, the same VD sat will be here, right? I mean, this will be what? Some gate voltage is present here. No, 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 no. Okay, this will not be in that manner. This is a good question. Okay, let's do it once. Hmm. This is a situation. So here, okay. So let's quickly do this now. What is IB? IB is 1 milliampere. Okay. So here we have to assume channel modulation is. We can neglect channel modulation for this. Right. So what is IB? IB is 1 milliampere. All the transistors W by L is 20. So gate to source voltage is what we know that IB is equal to mm, half mu n C ox W over L times VGS minus VTH the whole square. VGS of what? It will be VGS of M1 M2 sorry M2 minus VTH the whole square. So IB is 0. IB is 1 milliampere. 1 into 10 to the power minus 3 is equal to half into 0.1 to 10 to the power minus 3. W by L is 20. Okay. VGS minus VTH we don't know. Okay. So how much will this be? 2 and 10 gone. So this both of all this is gone. This is this much. So VGS minus VTH is equal to how much? This is 2, right? Or rather 1, sorry. So VGS of M1 is equal to how much? 1 plus VTH, which is 2 volts. Right. So this is what you were getting, right? 2 volts.
Yes.
Yeah.
Yes.
So this is 2 volts. So this guy has to be 2 volts. Okay. So how much is this? This is also 2 volts. So if this is 2 volts, so how much should this be? All the MOSFETs are anti-current, same current is flowing, right? So this has to be 4 volts, right?
Yes.
And if this is 4 volts, this has to be also 4 volts. So this also becomes 6 volts, right? So this also
6.
becomes 6 volts. So now that we are on this, if this is 2 volt here, and so tell me what will be the voltage here? Sorry. Because if this is 2 volt, the
Mayank,
current that is going to flow through this guy has to be how much? The same, right? IB, right? Because we are neglecting channel modulation here. So how much is
Mayank,
this? Yeah.
here like in order to keep VGS constant, that's why like here it becomes 2, then it becomes 4, like that,
Yeah,
right?
yeah, yeah, correct, right. Because same current is flowing, right? Through
Yes,
all the
yes, like it
MOSFETs.
depends on VGS, right? That's why.
Yes,
Like
exactly.
VTH is anyway a constant, so
Yes,
that's why
yes,
it's
yes,
okay.
yes. So tell me what will be the voltage here? Because the current, you know that because of this 2 volts here, and we are neglecting channel modulation. So the current through M1 will be what? The same, right? As the current will be same, right? IB, isn't it? Right?
1 milliampere.
So it will be, so basically the same current IB has to flow through all the three MOSFETs, right? So what is the minimum voltage? Sorry, what is the voltage that is going to appear here? What is the voltage that is going to appear here?
VGS minus VTH.
So it will be same 2 volts, right? Because This is 4 volts, this has to be 2 volts, otherwise there will be a problem, right? Am I correct?
Mank, it should be VGS minus VTH.
So that's what I, oh, no, exact, tell me why should it be? Why shouldn't not be 2 volts only?
If if it is in 2 volts, then it will be in off state, right?
Why? I'm talking about this MOSFET here, this node voltage.
It
The
should be
current through all the three MOSFETs has to be same, right?
yes,
The current through this MOSFET is how much? The same as this current. The gate is same, right? So this drain voltage we cannot directly find out, right? Because we have assumed channel modulation is not present. So we have to look at the upper MOSFET, this M3. For M3 to have the same current as M4, how much has to be the gate to source voltage? Same as M4, right? M3 and M4 are identical. So if they are having identical currents also, the gate to source voltage has to be same, right? Isn't it?
How to find VD for M1?
like how I have taken is like VD for M1 is like VD should be greater than like minimum it should be VGS minus threshold, right?
True, that is minimum thing is true. But I am saying that it also has to the current relationship also has to be followed, right? So okay, let's go through your way, okay, right? So you're saying that the current through so voltage at this point should be how much? 1 volts. That is what you're saying, right?
Yes, like 2 minus 1.
Okay. Now tell me what happened to the VGS at this point for M3. What has happened with the VGS of M3 in that case?
It is increased
It is increased, right? However, the current here is how much still? The current still is how much?
1
1
milliamp.
milliampere.
1 milliampere only, isn't it? And for 1
Yes,
milliampere, we already saw that VGS has to be 2 volts, correct?
Yes.
So there appears to be a contradiction, right, for M3. For M3, the VGS is now 3 volts. However, the VGS had to be only 2 volts for the same current. So there is a contradiction, isn't it?
Oh,
So this
uh,
will again be 2 volts only. Okay.
okay.
Yeah. And how much will this be in that case? Again, look at M5 and for M5. So M5 also it is for looking at M5 it will again become 4 volts only, isn't it?
Okay.
Yeah. So now tell me what is the minimum voltage that V0 can have so that all transistors remain in saturation. Because now VO has the freedom to move, right? Because VO can become anything. Now it does not have to worry about current being VGS being changing, VGS changing, right? Now VO can move up or down. So what is the minimum voltage that VO can have so that all transistors remain in saturation? It's very simple, na? If VO goes down, if VO becomes less than equal to how much? 6 minus 4 minus VTH, right? Right? 6 minus 1 volt, right?
Yes.
So VO minimum how much? 6 minus 1, isn't it?
6, 5.
I think
5
it should
volts.
be 6 minus 4 minus 1, right?
No, no, that is VDS. That is VDS. So I'm talking about VO. That is VO minus 4 volt. VDS has to be less than, has to be greater than or equal to VGS minus VTH, isn't it? Okay, the current condition is VDS has to be greater than or equal to VGS minus VTH, which if you write it like this, VD minus VS has to be greater than VG minus VS minus VTH. So source and source gone. So VD has to be greater than or equal to VG minus VTH. Is this clear? So this is what I have done here. What is
Okay.
VD here? VO min has to be greater than VG is how much? 6 volts minus VTH is how much? 1 volts. So this is how much? Got it?
Yes.
Hmm. Any doubts here?
Yes, Mac. Yes.
I don't think there should be any doubt here. Okay, fine, good. Now this is the minimum voltage at that the drain of this transistor M5 can go, right?
Yes.
Huh, good. Now the second question was if VOQ, basically the this voltage here, VO is equal to 6 volts, then uh, and then VO changes from 6 to 7 volt. How much does the current through M1 change? This was the question, right?
Yes.
So tell me. It solved it, right? You guys have done the assignment, right? How did you do it? How did you do it?
I got wrong answer for this.
I mean, what was your attempt? I mean, you also saw the solution. So did you understand the solution? Okay. So there are two ways to do it. Okay.
Okay.
This was one, right? Hmm. Yes. The second one. VOQ is equal to 6 volts, and now from 6 it increases to 7 volts. So in that condition, it was asked to you how much as voltage changes at this point. Because if the voltage changes here, right, then in that condition the voltage will also change here, and then voltage will also change here. So the question was how much is the voltage going to change at the drain of M1. So there are two ways to do it, right? One is to write this equation for all the transistors, right? The current to voltage relationship, which is IDS is equal to half mu n C ox W over L. Because you cannot neglect channel modulation here, you will have to also include that effect. VGS minus VTH 1 plus lambda VDS. This is one way. You write the equation for all the transistors and then solve it. And then you will exactly find out how much is the voltage at this point and how much is the voltage at this point. You will be able to find it out. So, were you doing it in this manner only? Did you try it in this manner only?
This is with like when CLM is considered, right?
Yeah. So, did you do it in this manner only, the way that I just suggested right now? Or did you do it in a different manner?
Yeah, I tried to basically find out through the uh, I think output resistance formula,
Yeah, yes, that is only
but
what we have to do.
goofed up, I think.
Ah, okay,
So
no problem. That's fine. But you see, if you try to attempt it in this manner, okay, which let me be very frank to you, when I did it for the first time, okay, like 3 years ago, 3 or 4 years ago, this problem I did it also in the like 4 years ago. I attempted it in this manner only. Okay, I wrote the current equations for each and every MOSFET, and then I tried to solve it. I was I got such huge equations that I was not able to solve it. Oh, by the way, I forgot this thing, Sana. This is a square, right? So it's a quadratic equation here. And it's a very messy thing. We will not be able, even I at the final stage, I don't think I even got any answer because the calculations were so complex. I was not able to get anything out of it. Okay, so this is I mean this way only computer can solve it. You can also solve it if you have that much of time. So this is not advisable. So what you can do is you simply start you simply understand that we can replace this assume that this MOSFET can be replaced by a small signal model like this. So each and every MOSFET is also accompanied by its own output resistance. So for simplicity, I'm not making another circuit and then drawing it. I'm just putting it here itself. You understand that this is small signal. This thing I'm talking about. This is R out 5, or for simplicity, I just RO5. This is RO3, and this is RO1. Okay, this is the picture here. And MOSFETs, we know that MOSFETs, yeah, in the small signal model you can draw it, the small signal model for this. And in the small signal model, what happens to the voltages here and here and here? So tell me, how will the small signal model of this look like?
Mac, like even in the first method, we'll get the answer actually.
You are getting the answer in the first method only.
No, no, no. I wanted to ask whether we will get answer like in that first method also.
You will get answer. You will get the answer if you are able to, if you can bear the pain of making the equations, writing the equations. Because here you see IDS, this equation has to be written for M5, M3 and M1. Okay, and then you have to equate a whole lot of voltages here and there. It becomes very messy. I
Okay.
can tell you from the experience, because I did it 3 or 4 years ago. When I did it for the first time, when I was learning this course for the first time, I did it myself, and it was a very painful job. And at the final stage, I because I did some mistakes in the calculation, I was not able to get anything out of it. But it is not it. Having said that, it is not. You will get an answer, okay, out of it, because when computer does it now, computer solves it everything in this manner only. Computer does not know what is the small signal and all. Computer always does it with the current equations only. So current computer does it. It's just that we as human beings are very lazy to do it. Okay, so we have to find smart ways to do our job. Getting my point? It becomes very messy in this manner.
Yes, yes.
Yeah. So yeah. So tell me, how will the small signal model of this look like? So as I just said, M5 can be. So I'm see MOSFETs. I'm replacing with their own MOSFET only. Okay, I'm just replacing it with this MOSFET itself. So this is like this. It's just that I am putting a resistor like this. This is one. This is two, and then there is three. There are three MOSFETs, right? So this is RO5, this RO3, and this is RO1. Okay. Now tell me, what happens to the gate of these three MOSFETs. This is ground, by the way. Yeah, so what happens to the gate of these three MOSFETs? What will be the voltage here? What will be the voltage here? Tell me.
2, 4, 6.
The MOSFETs will be connected here, right? 2, 4, and 6. But tell me something. Uh, how do I explain it? This is a small signal model, right? In the small signal model, or incremental model, small signal or incremental, right? In the incremental model, all the voltages which are not changing, right, which remain fixed, we say that they can simply be made to ground, right? Put
Yes,
to ground,
got it. Yes.
correct? So tell me, will this voltage change or not? Will these three voltages change or not? These three voltages.
They are fixed.
They remain fixed, right? I mean, change by change, I mean if you apply any change in the circuit here and there, if you apply any change in the circuit at this place, because this is your place of interest, right? This place here, you will be applying something. You will be applying some incremental voltage here. So because of this, can the voltage change at these three nodes here? Yes, tell me. Because of any voltage change at this node, can the voltage change at the gates of all the three MOSFETs? Can that happen?
No, I guess.
That is not possible, right? So these three node voltages, they can be said that they are incrementally shorted to what? To ground, right? This can be said about them. So this is what we are going to do. This is ground, this is ground, this is also ground. Okay, and now we have this MOSFET in place here. Okay, so and we have some voltage change here, right? So this is like incrementally we are going to see, right? So its voltage changes from 6 volt to 7 volt, right? So what is the incremental voltage that we are going to apply here?
1 volt.
1 volt, exactly, right? Because from 6 to 7 there is an increment of 1 volt. So because of this, how much will the current I test, or yeah, so I test you can say, how much will be I test? This is what you have to
One.
find out. Okay, you'll be able to find it out because we know that each model will be replaced, each MOSFET has its own GM, right? So this I have, so let's say this has a GM of this is, oh sorry, this will be some GM 5, this will be GM 3, GM 1. Okay, so each MOSFET has its own GM. Okay, and then there is I test. So you have to find out how much is the I test. So that you can do, right? You can do it, right? You can do it, isn't it? Okay, so one easy way to, or generalized way to do is that you can here we have assumed that there is some increment. We have exactly found out how much is the incremental voltage, right? So it is 1 volt, and then we will find out how much is the current, and we'll simply do everything, right? Once we find out the current, we will be able to find out every voltage here. So we will be able to find out voltage here also. We, let's call it VD1. This is VD3, right? So this is 1 volt. So VD3 we will get, VD1, all we will get, right, because of this. But uh, other than this, I also want to tell you here is that if you find out how much is the output resistance in this particular circuit, that is, so in this circuit, if you try to find out how much is the output resistance, so how will you find out the output resistance? You apply a V test and you find out I test. So R out will be V test upon I test. Correct? This is your R out. So if you find out R out, how much will be R out? Tell me. Did you do it? Did anyone try this? How much is the R out for this?
Yes, we have tried it. So ROT
One second, I
is.
am not able to hear anything. Something.
Yeah, am I audible?
Can you please speak again, Nikhil?
Yes, I have
Yeah,
calculated it.
yeah. Tell me how much is this?
1 minute. Yeah, it is actually
It will be a
uh,
complicated expression
yes,
slightly.
RDS3 plus
R out will be RO3
I
plus
okay, RO3 plus GM2
GM2.
RO1 RO2.
It's in. Where is GM1? GM2 here. This is
I
M1,
mean,
M3, and M5.
okay, I have taken like okay, that is GM3.
Okay, so GM3.
So how did I take it? Okay, GM3 and GM1. Sorry, GM3 into
Uh,
RO1 RO2
RO1, RO3.
RO RO3, yes.
Yeah.
And last term is uh, GM5 GM3 into RO1 RO3
GM5,
RO
GM3,
into R1.
RO5, RO3, RO1.
Yes.
Is it correct? I don't think so. No, it is correct. It is correct. It is correct. Fine. Good. I think it is correct. So you can see that. I mean, generally, if you do it like this, RO3 plus. There is a slight error, I think, somewhere you have made. There should have been some terms equal to RO3 plus RO5 plus RO1 also. You should have also gotten a term like this plus RO5 plus RO1. Didn't you get that? Didn't you get this?
No, man, I think I have not got it.
There's some error. Try to look at it, okay? You will get another term, other terms also. There's some error here. So anyway, it doesn't matter much because ultimately the term that will dominate will be this one. Okay, this will dominate. So here you can see that the the correct way to write is this way. It is GM 5 times GM, or rather RO5 into GM 3 times RO3 into RO1.
Like once can you explain how to find out this? I have done using like uh s- like what if based on like two connections was explained, right? So based on that I tried
It's
it
very
actually.
easy. I mean, just write KCL and KVL. You will be able to find out how much is the RO. You will be getting. You should have gotten other terms also. Okay, RO3 plus and RO5. So there will be other terms also. Please try to do it. Do not make any assumption here. Just solve it exactly. You will be able to get. Okay, try it out. You will be getting something. You will get anyway. So this is here. So the term that will be dominant here is will be this term. Now, if you remember, for a MOSFET which didn't have which had only one layer of cascoding, so if this was not present, the net output resistance was how much? It was this much, right? It was this guy. So sorry, the dominant term was this guy, right?
Yes.
But because of this extra MOSFETs here, extra MOSFET GM5, the dominant term is now getting amplified by another factor, which is the gain, intrinsic gain of the uppermost transistor, isn't it? So in summary, what I'm trying to say is that the moment you start stacking the MOSFETs on top of each other, the output resistance is getting amplified by the intrinsic gains of each MOSFET. Okay, this is what I'm trying to explain here. So you see the gain of intrinsic gain of MOSFET number 5 is coming here. Then the intrinsic gain of MOSFET number 3 is coming here, right? So and then and this is, these are the intrinsic gain, and the R01 is the output resistance of the first MOSFET. R1 is the output resistance of first MOSFET, right? So R01 is appearing here. So R01 is getting amplified by the intrinsic gain of the MOSFETs which you are stacking on top of it, and that is becoming the net total R out which you are seeing, isn't it? So this is what is happening. This is what I meant when I said that because of each stacking, you are simply improving the output resistance of your current source and making it a better and better current source. Also, I would like you to try this also.
Like how I have approached that, like to calculate this ROT is like this is there, right? Which dominant term of two, like a single cascading.
Huh.
So that I take it as like
Oh, acha,
R
acha.
R
That is
into that.
why. Okay, okay, I got
That's
it. I got it. I got it. But don't do that. Okay, don't do that. You will get the correct dominant term, but you will miss out on small non-dominant
yes,
terms.
exactly. That I have missed it.
Yeah, so don't do that. Do not make any assumption here. Solve it exactly. Will get other terms also. But anyway,
Okay.
this will be anyway the dominant term, so no worries there. It's fine. So next point that I wanted to wanted you to understand was, I also said that because of each layer of cascoding, what is going to happen? What is going to happen? As I said earlier, is that the MOSFET,
Out, output impedance will increase. Like
that is fine, that I told, but I also said that each layer gives a protection, right, to the layer below it in terms of the swing that is happening, right? So what I was saying here was that if this guy is swinging by this much, this guy here is going to swing by a small amount, this much, and this guy will be very small, correct? This is what I was saying. So you can clearly see that, you see, because of 1 volt change here, because of 1 volt change here at the output side, try to find out how much VD3 is changing, and then also see how much VD1 is changing. So those guys who have solved it, tell me, how much did you get for VD1? How much change were you getting for VD1? Has anyone solved it? So anyway, try it, try it. I mean, I will not solve it. It's too much here to do it. VD1, so you can do it quickly, right? If you find out how much is the R out here, you know that R out is the dominant term here, right? So because of this, you know how much is the R out. So you also know how much is the current, right? Because of V test. So you can quickly do it here in this case. So R out is how much here? R out is already known, right? This is the term. So how much will be the I test? Because of this 1 volt, how much is the incremental current? So don't call it I test, call it I incremental. Okay. How much will that be? It will be 1 volt upon R out, isn't it? Am I correct?
yes, yes.
Yes. And when you have this I incremental, once you have this I incremental, you can find out the voltages at each node, right? You can find out voltage at this node VD3 and VD1 also. So how much will be the VD3? VD3 will be I incremental times R out, which is at this node, right? Looking below it. Try it, okay? And then this will be higher, right?
That will be one total voltage minus this, right?
One minus I guess.
One
Come again?
minus I increment dot R out
Where?
at VD3.
Why do you say that?
Yeah, that is why I have confusion. So basically, if you consider that as a resistance R05, so
Hmm.
there must be the voltage drop.
No, no. This. Okay, okay. Let's do this.
Mayank, like for every transistor, we need to like small signal needs to be drawn, right?
Yeah,
For
yeah,
everything,
correct, correct.
like
It has to
then
be,
we have
yes.
to analysis like
Yeah, yeah,
R out.
yes, that is true, yes.
Okay, okay, I'll try it.
So coming to this point made by Sakya. So tell me, Sakya, how will this look like? This will be 1 volt here, okay, and you have first this is R out, earlier R out, right? So let's call this R out 2, okay, this is R out. So this was the earlier the first case, right? From here you can get how much is the I incremental, correct? That is going to flow through this. So this whole guy, this whole thing here is replaced by this R out, correct?
Yes, yes.
Yeah. Now once that has happened, now what I'm saying is now the current is moving, okay? Current is going inside. You know how much is the current that is going to go inside. Now what I'm saying is, okay, let's do this here. Once you know how much is the current that is going inside, tell me the current that will enter here and here, will they be I incremental only or something else?
Yes, yes, it will be I
I
incremental.
incremental only, correct?
Yeah.
So once I incremental leaves this point, so this is the first MOSFET and it's whatever it is. Once I incremental look goes inside this, okay. So now again it can be replaced with some R out, right?
Okay, so basically you are saying the same current is moving
Yeah.
through the all
Yes.
stages, so voltage, potential voltage difference will be
Yes.
same.
No,
So
no, no, difference will not be same, but it will not be. So this is again plus 1 volt, okay, and this is I incremental. So what will the voltage that will appear here at this point? It will be I incremental into R out, isn't it? Why should it be minus 1 minus something? 1 minus something will be the voltage across this one, na? Across this one.
Yes, yes.
But
Okay,
the
yes, yes.
exact voltage here will be how much? This will be 1 I incremental into R out.
Yes, like rest thing is grounded, right? Another voltage.
Huh,
Okay, yes,
correct,
yes.
isn't it?
yeah, I have to again.
No, no, think about it and try it.
So
Okay,
basically,
try to solve
you
it.
are so what you have drawn is basically, let's say it is a voltage divider circuit, right?
Yeah, it's
The
a
R
voltage
raised
divider only. It's a voltage divider only.
so then the voltage there should be I increment by R out 2.
Yes, I went into R out 2.
Yes, I increment into R out 2.
Yes,
And R out 2 is your R GM3 into that small portion
yes, yes,
contributing the
yes,
lower two
yes,
transform transmit.
yes.
Okay.
Mayank here, one more doubt is
Hmm.
RO2 is that effective, like what you call output impedance of both transistors, right? R03 and R1,
Yes,
correct, right? So it will
yes,
be effective impedance, like
yes,
total
yes,
impedance of
yes.
R03 as
Exactly,
well as
yes,
R01, like two
yes,
MOSFETs, 3 and
yes,
1.
yes. So if from here only you can see that the since R out 2 and R out, they have what I mean if we only look at the dominant term, so this is R out 2, right? This guy is R out 2, this guy is R out, isn't it?
Yes.
So in this you can see that between R out 2 and R out, what is the how much is the factor difference? How much is the difference in terms of factor? So this is R out, this is R out 2. So R out is greater than R out 2, right? That much is known. So by what factor it is greater than R out 2? So
By
this guy is,
GM5, R05.
yeah, so it is GM5 times, so this guy is GM5 times R05, isn't it? Correct? So this is what you can see clearly. So how much ever I incremental is, at the first stage you will get some swing, right? Because of R out, you get a 1 volt swing. At the second stage, how much will you get? Same I incremental is flowing through R out, but now R out is smaller compared to R. I mean R out to this guy here is compare. Am I still there? Am I visible and audible to you? Am I not? Am I audible to you now? Okay, okay, it's fine.
Yes, yes.
Yeah, there was some issue with the internet connection. Anyway, so I was saying that. Tell me what will be the voltage at this point? It will be I incremental times R out two, right?
Yes, yes.
This is VD3, right? So VD1, or rather V out, VD3 is equal to I incremental times R out 2. And again, similarly, what will be VD1? It will be I incremental times R out 1. Correct?
Yes.
Yes.
So now tell me how much will be, and how much is I incremental, by the way? I incremental is how much? It is 1 volt upon R out. Correct? So from here, if you replace it here, what will you say? VD3 is equal to how much? 1 volt into R out 2 upon R out, right? And what is VD? Uh, VD1.
Okay. By this, like it will be simplified.
Yeah, so it is R out 1 upon R out, isn't it? Is this correct?
Yes.
Yeah.
Yes.
So you can see clearly, and we know that. So R out 1 was how much? So R out 1 by R out will be how much? So this is R out 1, right? R out 1 is simply RO1, correct? R out 1
Yes.
is equal to simply RO1. So you can clearly see this will be a very large factor, isn't it? GM5 times RO5 times GM3 times RO3, correct? How much will this be? 1 over GM5 times RO5. So you can clearly see that it is keep on reducing, right? VD1 is very small, right? This because this factor is very large. 1 over something is very small. This guy here is very large compared to this guy, right?
Yes.
You can see
Which
that.
means like incremental swing is less
This is what I was trying to say.
in the
Yes.
case of
So this is what I
VD1.
was trying to say earlier also.
Okay.
That as you keep increasing the as you keep going down further down the layer of protection, you will see that the swings are keep on reducing. So this stage it will be highest, then here it will be slightly smaller, and here it will be smallest. This is what I was trying to say. Okay.
Okay.
Yes. This is what I was trying to say. So I think I covered almost everything. Yeah, I have covered almost everything here. So one thing that I've not covered here is what is basically is a simple thing is that basically if you change the WYL of things here and there, so some things will change. So that I
Overdrive voltage. Overdrive will
overdrive voltage
change.
and change, those things will change. So because of that, what will happen? That you have to understand. So that let's keep it for next time. I don't think you should have faced any problem here. Did you face? So this is basically the whenever we draw current mirror, we generally don't show anything here, right? We just ignore what is happening at this point. We just keep it open here. We were keeping it open here, right? We just put a terminal here and said that something might be connected here. So that something is connected in this place in this particular question. A load is connected here, okay? And then the question is asked. So how much current can you have so that your device does not go out of saturation? So I don't think you must have found any issues with this question.
Yeah, it was simple.
Yeah, the whole point was to make sure that you understand that something is connected there, okay? You see, I will tell you what is the problem from my personal experience. When I was I was a UG student in my second year. When I learnt about this current mirrors thing, and it was always shown in this manner only. So I never and what ended up happening was I used to think that nothing is connected here. Okay, I was under the impression nothing is connected here, and then I was always confused. So why then? How come there is some current flowing here? Okay, because I always was looking at this figure only. So I never used to understand how there is current flowing out in this when there is nothing connected. When this is just open, when this node is just open, how can there will be how can there be current flowing through this? So that is why this question was designed, so that you do not face that particular kind of confusion. That is a very silly confusion, but still some people have that. This guy is actually connected, okay? This guy actually connected to something. It's just that we have shown a generalized case here where this is just a terminal and it can be connected to anything. Getting my point?
Mayank,
Yes.
there we need to take that VDD minus IB into RL. That it should be equal to this minimum.
Correct. That is there. Yes. I mean for saturation condition. Yes. Because of this RL that is put here, there will be a drop at this place. Okay, and because of this, then this transistor here can go out of saturation. Okay, if you increase the current a lot. We have already solved a lot of questions in this of this type in earlier sessions, right? So this is fine. So I think that is all which I want to discuss today.
Like current mirroring happens like only when you have collected load, right? That is what you wanted to convey.
No, load. Yeah. So no. What I was trying to convey was that you see here it looks like it is open, right? Nothing is connected at the output, isn't it? This is how it looks like. Are you there with me?
This circuit is basically representing if the output load is infinite.
No, it is not
RL
saying
is
that. No, it is not saying that. It is saying that we don't know what is the load. Okay, it's just a terminal. Okay, and there is a actual figure should have been like this. Okay, we don't know what is connected here.
Okay.
okay.
Yeah, we don't know what is connected here. There will be something will be connected here. It's just that we don't know what is connected here. And yeah, for solving the question, yes, you assume that the load, whatever will be connected here, will have infinite impedance. Yeah, for solving this question, that you have to assume. But actually, we do not know anything about it here. It's saying that something will be connected here. It's just that we don't know what will be connected here. Okay.
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 Yeah.
Mayank,
So,
I have a doubt.
huh.
The assignment number 8,
Okay.
and it is the first question. Your bias saturation with constant voltage and constant current, and that
Yes.
part.
Huh.
So constant current, I understand, but constant voltage, that calculation, whatever you provided in the solution, that part I did not understand.
This is the assignment, right? So,
Yeah.
what is the question here?
You already provided the solution. I
So, I don't write the solution. Solution is written by someone else. But tell me, what
Okay,
is the
okay.
problem?
So I did not understand this the middle two part.
Metal 2 means third, fourth, fifth, which one?
Uh, no, so it will be third and fourth.
Third and fourth. For a MOSFET biased in saturation with constant VGS, GDS is directly proportional to 1 over L. So what is GDS equal to? GDS equal to, it is written here also, right? Lambda n times IDS, right? It is lambda n times IDS. And tell me
Yes,
what is
yes,
IDS? What is
yes.
IDS? IDS is equal to 1 plus
One
lambda.
milliampere, right?
Come again?
What?
No, 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 not
IDS
that.
is directly given as 1 milliampere.
Where is it?
No, no. We have to calculate the IDS and then we
Ah,
have to put the value of lambda and 1 by L. So basically that, so how did they arrive at that
no, 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 no,
conclusion?
no.
I did not understand.
This is not
So
that. Huh?
you can open the,
I'll tell you. So what he's trying, this is just you can get from the expression itself. So you have IDS. So sorry, what was the question? A statement was for MOSFET biased in saturation with constant VGS, right? This was it. So with constant VGS, what is GDS equal to lambda times IDS? Okay.
yes,
What is lambda IDS? IDS is equal to mu n Cox W over L by 2 VGS minus VTH whole square times 1 plus lambda VDS. This is what it is, right?
okay.
This is what it is, isn't it? This is what it is.
Mhm.
Okay. So tell me now, uh, this guy here. Let's say you can ignore this in finding out the IDS. Okay. This guy here you can ignore in when you try to find out what is IDS, because this will not impact much. So let's ignore this. So how will this look like? So lambda is how much? Now it is already said that lambda is inversely proportional to L, right? So it is
Yes,
some
yes,
k
yes.
divided by L, right? And it is mu n Cox by 2
That
times
is
W
also
over
constant.
L.
Okay.
So VGS minus
Okay.
VTH the whole square. And you know that this is constant and this guy is constant. So it will be how will this look like? GDS will be some k prime times divided by L square, right?
L square. Okay, okay, okay.
So it is
Okay.
GDS is proportional to
Proportional to L's 1 by L
L
square.
square, right?
Okay. Mm-hmm.
So
Yeah.
this is how you have to do it.
I did not I did not remove that 1 plus that part,
Yeah, I mean,
lambda part.
yeah, you can ignore this as long as there is, I mean, because 1 plus lambda IDS is very, because lambda will be always very small. Okay.
Mm-hmm.
Lambda is very small in for good transistors. Lambda is very small, and when even if it is getting multiplied by VDS, it will be very small compared to 1. It will not add much to 1. Okay, it will not add much. The impact of lambda will only come because of, so you can see it here, right? Lambda comes directly here for GDS. You can ignore lambda
Okay.
to the first order in this.
Thanks. Thanks.
Yeah, it's fine. Yeah, and fourth, and you also had doubt in fourth, right? No, no.
No,
Uh,
it is the same.
oh,
Either
third
1
and
by
fourth are
lambda.
same.
Yeah.
Okay, okay, okay. Fine. So I think that concludes everything which I wanted to discuss today. So it's fine. Then we will discuss. We will meet again on what next? The Tuesday. Fine.
Yes, ma'am. Thank you.
Yes. Yes.
Welcome.
Okay.